So on page 83, we wish to estimate the percentage of U.S. adult population that has hyperthyroidism. A random sample of 400 U.S. adults shows that 46 have the disorder and require medication. Okay, so what is the population of interest here? Who are we looking at? Who do you think?
The people with hypothyroidism.
It's the U.S. population. But we're testing to find who has that, but we're looking at the U.S. population. So what is the sample? The sample is how many people?
400.
Yeah, 400 U.S. adults, right? And then the point of estimate. This is where, so for number 3, to get the point of estimate, we saw that 46 out of the 400, 46 out of the 400 had it, which you got to double check my math. I think that's right. 23 out of 200. Is that right? Did I do that right? All right. So we are estimating that basically 11.5% of the U.S. population adults has this disease. Now we're not sure about this because we did a sample and it said a random sample, and 400 is a really good sample, randomly sampling people. So it is very possible we're very close to the number of people with this hyperthyroidism. Okay? And then it says we want to construct a 95% confidence interval to show in the context. Okay, so can I move off the screen?
Yes.
All right. Hush down over there. All right. So number 4, we want a 95% confidence interval. Okay. All right. So what I'm going to do is, remember, we're doing that. That's exactly what it is. I'm trying to think, where do I want to go with this one? All right. So this is where we're going to have to do that inverse norm, or inverse CDF, I think it is. Okay? And this is where it becomes halfway to 100.
So it's like 95, so it's 97.
Yeah, very good. So I'm going to plug in here the 97.5% or a 0.975. Okay? All right, so what did I do? Okay. Desmos. So Desmos, we have DESMOS. All right, so again, I think this is kind of cool. So remember, you got to go normal distribution. And again, the new trick, I think this is kind of cool that I never knew this worked. But if you do that, that satisfies doing the 0, 1. If you don't know what the mean and the standard deviation is, it's going to give you your normal curve very nicely. And that just automatically defaults to that. So I thought that was a neat feature. And then I do a period, which the graph goes away, and that's okay, correct? And then what I need to do is I need to find my inverse CDF. And we're plugging in 0.975. Is that right? Yeah. So now that's our z-score. Does that make sense? But the problem's not done at this point. That's our z-score. So our z-score is 0.9, or what was it?
Go back.
I forget. 1.96 rounded. 1.96. 1.96. So that's our z-score. So then we're going to go, it's z times, trying. I knew it was going to freeze up as soon as my hand hit that p. 1 minus p over n. So we know the z-score, so that's 1.96. And then our percent of these guys was 0.115. And then this is going to be 1 minus 0.115. And our sample size was 400. We got that 0.115 because we took our 46 out of 400. 46 out of 400 is 0.115. So that's going to work out nicely for us. to plug this in. And then remember, that's multiplied right there. Is that okay so far?
What's the 1.96?
The 1.96, that came from Desmos, where I had my halfway, I do normal diffs. I don't have to have 0 and 1 because that'll default to it automatically. And then you go period inverse CDF. And then the 95%, because we want a 95% confidence, we're going to go halfway to 100. Halfway to 100 puts us at 97.5, which is 0.975. And so that's, this right here gets our Z-score. Does that make sense?
Yeah.
Okay. So then I'm going to do it on here and just use a calculator. So I'm going to go 1.96 times, and then a big square root. And I have, I'm going to keep this in parentheses. So I go 0.115, close parentheses, open parentheses, 1 minus 0.115, close parentheses. And then if I go divided by, this should work out. Yes, it did. And we have 400 people total. Oop, not 4,000. 400. So we have a confidence, our confidence interval is going to be roughly plus or minus 3.1%.
What is it?
It's right here, plus or minus 0.031, which is 0.31% or 3.1%.
Where was what did you get 0.115?
The 0.115 was our point estimate. That was the 46 that had the disorder out of the 400 we tested. So we got to 0.115.
So you just divided.
Yeah. All right, so 3.1 we said? So plus or minus 3.1. Come on. 3.1. And we go 11.5. These are both in percents. You can keep this as a percents or not. So that's going to take us to 50. I'm off. 14 what? 14.6. And then the bottom end is going to be 11.5 minus 3.1. 8.6? $8.4. That's okay. You added one, subtract the other.
So it's like the combination of the lower and the higher.
Right. All right. So this was our point estimate. This is where we found basically our margin of error, our confidence interval. Okay. And the confidence interval was found with using this. All right. So what this means, we are 95% confident that if we went out and sampled another 400 random U.S. people to test for this disease, so we're 95% confident that if we were to go sample another 400 people with this disease, that their 11.1, oh wait, that's right. That the 11.5% that we're trying to target, we're going to fall. We're 95% confident that we will fall if we test those 400 random people again, or another 400 people, that they will fall between 8.4% to 14.6%. Okay? Now, this is one thing you have to understand about how this statistics works and why it works. I set a key there. If I go, so let's say I work for a major drug company.
Which one?
We'll go Pfizer.
Okay.
Okay? So let's say we're working for Pfizer. And Pfizer reads, they know that they're in competition with Moderna and Johnson & Johnson for this new medication that's going to be revolutionary. So what they want to do is they're going to run through it, and they're going to take a look at what their data is and how do they collect their data. Oh, so maybe they even do it. Even take it one step further. the CDC, the Center of Disease Control, is actually going to look at these statistical tests over and over and over again, and they're probably going to hire out, because CDC is federal government has a lot of money, federal government could go and hire people to go and run random surveys, so they want to see if this is truly in the ballpark. Okay? So if I continue to do 400 random samples of people throughout the United States and test them for this disease, what's going to happen is this 95% might still be 95%, but as this continues to grow, this is going to get closer and closer and closer to the 11.5%. That's the main foundation of what we're doing. Okay? Now, so I want you to think about something here. This portion right here, where we have 1.96 times the square root of 0.115 times 1 minus 0.115 divided by our sample size, as this sample size gets larger and larger and larger, okay, so if I made this 4,000 or 400,000 or 400 million trillion or whatever, this gets really small. I mean, take a look here. That 1.96, that's our z-score, okay, of 1.96. So 1.96 is almost 2 standard deviations out. But if I go back to Desmos and I just change this and I say, well, let's make that 4,000, look what our z-score changes to. It gets a lot smaller. If I go, 40,000, if I go 400,000, if I go 4 million. So that changes, that score will change very nicely for our z-score, which means our multiplying value to get our margin of error here, as 400 or n increases, this value here becomes smaller and smaller and smaller. Okay, which is great, because the more you do in a random sample, the more confident you are as you are approaching what they call a census, and the census is 100% of the population. Okay? But let's face it, if it is just me going out to do a random sample of 400 people throughout the United States, am I spending a lot of money and a lot of time? I guess it depends how I sample them. Okay? I could have a random phone number generator on a computer, and I could dial numbers and try and get a hold of people to collect data. And I was telling somebody about this the other day. We all have some sort of feature on our phone that might say potential spam. Right? My wife's name on my phone is potential spam. I'm just kidding. So it's getting harder and harder and harder to do a survey over the phone, because we've got so inundated with so many different calls. I mean, let's face it, when you first got your cell phone, you were excited when you get your first phone call or your first text or whatever. You were young. Okay, it's like, hey, cool, it worked. Oh, that's neat. But now we've gotten to a point where it's like, I don't even want to hear from these people. I don't need somebody calling me. I got other things to do. I gotta check my InstaFace, Snap, TikTok, Yak. Stirp, what is that? I don't know. I'm just an idiot. Okay? You guys already know I was an idiot, so that's fine. All right, we're moving down to number 5. You with me? Number 5 says, does this confidence interval provide evidence to support the following statement? More than 10% of U.S. adults have this disease. Okay, so it's more than 10%. Well, our 10% falls within here, between 8.4 and 14.6. And again, I can't judge if I had done a study and I came out with 8.5%, even though it's to the left, it still falls within the parameter, which is fine. So does this confidence interval provide evidence to support the following statement? More than 10% of the U.S. adults have hyperthyroidism, and we have to say no, okay? Because if they said more than 8%, that's outside, that's the evidence to say yes. Because I said 10%, that's within our window, we have to say no. Okay, because again, I don't know exactly where between 8.4 and 14.6 are going to fall. I might, if I keep doing this, I mean, I was trying to get to 11.5%, which is in the middle of those. But I'm not quite sure if I'm exactly right or wrong. So if they're asking, is there evidence? You guys went to the East Cafe or something?
There was a line.
Oh, line.
There's a line.
Yeah, they went to McDonald's. They didn't get us anything.
All right. Number 6, is the sample size large enough to meet the normality of the assumption? Okay, so problem number 6, again, we're on page 83. They want to know, is n times p greater than or equal to 10? And is n times 1 minus p greater than or equal to 10? So our sample size, we said, was 400. Bless you. Our p-value was p-value is 0.115. So 400 times 0.115, is that greater than 10? And is 400 1 minus 0.115, is that greater than or equal to 10? Well, if that was 100 yet, so yes, this is bigger, so this checks. I don't even have to do the math because I know that 400 times just 0.1 is 10, so that's going to make it so 400 times 0.11 is bigger. And then this one, I mean, that comes out to 88.5, 0.885 times 400, that's also bigger than 10. So this does indeed support that we had a large enough sample size for our proportions. Okay? If we had said 40, we might not be there. If we had said 30, we might not be there. Again, you just have to do the math using these two equations. Okay? Now you remember, we've kind of, I had said quite a while back, you want a random sample of 30, which is accurate, which is great until you start dealing with proportions. Then you have to start looking at the n times p is greater than 10 and n quantity 1 minus p is greater than or equal to 10. The critical value for 95% confidence. So our critical value, number 7, is that 1.96. Okay, so this means if we were looking at that original thing, this was our z-score that we found. Okay, this means we are 1.96 to negative 1.96 standard deviations from the mean. That's needed. So because we have 1.96 standard deviations, that's what we need in order to get to 95%. Okay? Now, you remember when we first started the normal curve, we said 68, 95, 99.7? That's where that 95 came from. 1.96 rounds to 2. 95% is roughly 2 standard deviations above and below the mean. But this is a more accurate picture of it because now we are learning more. State the margin of error. So the margin of error is basically 0.036 or that's not what I have. It's, what did I have? Let me see. 0.31. 0.31 or 3.1%. Okay, that's our margin of error. Briefly explain what would happen to the margin of error if the confidence level is increased to 99%. What do you think? Margin of error increases to 99%. What's that going to do in this case? So if this becomes 99%, this here is bigger. Okay? We spread out further and further and further, and we could easily go through and find that where if we wanted 99%, we could do the inverse CDF to halfway to 100. So you go 0.99 to 0.995. That's halfway to 100. Do that. So the margin of error would increase. And just about done. Actually, you know what? You do me a favor. I am going to, let me make sure I'm on the right page. Will you do me a favor? Because I know many of you are on this, you're paying good attention. Will you make sure page 84, that's an 8 and that's a 4, 10 and 11, give it a good try for tomorrow. Okay, that's all I want you to work on for tomorrow. I need to also tell you, friends, listen. If you haven't listened to anything all period, listen to this. I will not be here Friday. I'm bringing in a personal favorite person of mine. Mr. Mimak will be here.
No way.
Way.
Oh, I love that guy.
Me too. So, what I have on Friday is I'm gonna have you guys do a worksheet, which would have been a quiz, but it's not going to count for a quiz. But I want you to work on it during class. Obviously, Mr. Mimak can help you. And then just turn it in at the end of the period, whether you're done or not, okay? So they called yesterday. They need us up to our new house so we can, they want to do this walkthrough of all these things before they put the drywall up. Huh? I won't be here Friday, but Mimak will. So you got somebody better than me.